Be aware of the fact that when Einstein first came up with his idea of general relativity, it was a hypothesis. It was an educated guess, but it had not yet been tested. So how do we test general relativity? How do we test whether space-time is really curved by matter the way Einstein predicted that it was? There have been many tests actually of general relativity. It is an extremely well-tested theory for over 100 years. Let me just give you a few of them. So one of the first tests of general relativity was related to an observation that had already been made, and that was about the orbit of Mercury. Remember that one of the big accomplishments of Kepler's laws of planetary motion, and then more generally Newton's law of universal gravitation, was that it allowed the prediction of the motions of the planet so that we could predict far into the future, far into the past, where a planet would be at any given time. And this worked beautifully for all of the planets except for two. We already discussed one. Remember that when William Herschel discovered Uranus in 1781, its orbit didn't quite match what was predicted by Newtonian dynamics. And so people thought maybe there was a planet further out that was tugging on Uranus, and that would account for the anomalies. And the French astronomer Leverrier used the observations, to actually calculate where this mysterious planet should be. And so Neptune was discovered on paper before it was ever observed. The other problem planet was Mercury, and Mercury's orbit simply did not quite match what Newton's equations predicted for it. So if we think of this, imagine this line is representing the predictions that Newtonian physics makes, and for Newton, space, remember, is absolute. And so the presence of the sun, while it adds its gravitational tug, that gravitational tug will be the same throughout space, same in nature, not same in strength, but it'll be the same in character regardless of where the planet is, because space is the same everywhere. And so using Newton's laws of gravity, we could predict the orbit of Mars, and it matched what Newton predicted. The orbit of the Earth matched what Newton predicted. The orbit of Venus matched what Newton predicted. But then we got to Mercury. And Mercury was off by somewhere between 7 and 8% in the predictions, and that's a huge margin of error. People knew there's something wrong here. And one explanation they came up with, one hypothesis, was that maybe, like there was another planet beyond beyond Uranus tugging on it, and thus led to the discovery of Neptune, people speculated maybe there is another planet closer to the sun than Mercury that's tugging on Mercury and accounting for these anomalies, and that we just haven't observed it because it's so close to the sun that it's lost in its glare. They went so far as to name this planet. They called it Vulcan, and they spent decades searching for this mysterious planet that must be tugging on Mercury. But in decades of searching, they never did find it. And that's because it's not there. The real explanation, as we now understand it, is that Mercury is close enough to the sun that it's in a region of space that is affected sufficiently by the curvature of space-time produced by the sun that the calculations no longer match what Newton came up with. Newton's physics works perfectly if space is relatively flat. And so in the small gravitational well produced by the Earth, Newtonian physics works perfectly to predict what's going to happen to an object. And so we still launch our rockets to the moon and into space using Newtonian physics. We don't bother with the more complicated general relativity because the differences in our region of space are so tiny that they don't actually affect anything. But once you get close enough to the sun, like Mercury is, then it's in a region of the gravitational well of the sun that's being tugged sufficiently, being warped sufficiently that the calculated numbers from Newtonian physics no longer match up with the calculations from general relativity. And the amazing thing was that when they used the equations of general relativity to predict the orbit of Mercury, they matched perfectly with the observations. And so this gave us a reason to think that general relativity is correct.